anything that was not clear about Ellingham diagrams, the free energy considerations in the electrometallurgy? Any questions? The Solvay process, the Hall-Héroult process, the Pidgeon process, kind of talk quite a lot about these electrochemical processes. They're all industrially very important reactions. So I just wanted to make sure that you're all comfortable before we continue our journey into the electrochemical potentials and bring a relevance to the inorganic chemistry, because most of the time we're interested in the stability of the species, which species is stable in water, which is not stable, which will undergo disproportionation. We'll go into all those details. But before we continue in that direction, I just want to make sure that there are no questions so far. No? All right. So if there are no further questions, let's start doing some problems in the class. And I want all of you to turn your calculators on, even if you're not turning your cameras for whatever reason it is. But once we turn the calculators, we're going to do some problems in this class. So the first thing that we want to do is, let's talk about, I got some self potentials here. Can you all see the board? Maybe one of you can say yes or no. Yes, wonderful. Thank you.
I can.
Okay, all right, great. So let me write down a redox reaction. Let's say if I have dichromate anion, which is Cr2O7 minus, that reacting with 14H plus 6 electrons, giving 2 Cr3 plus 7H2O. The cell potential for this is 1.38 volts. It's a plus. So is this reaction spontaneous or non-spontaneous? The cell potential is plus 1.38 volts. What does that tell you about the spontaneity of the process? We all know delta G is negative in Fe, right? So if the potential is positive, the free energy is negative. So what does it tell you about the spontaneity then?
Is it non-spontaneous?
If the potential is positive, then delta G is going to be negative because delta G is negative NFE. Neither N nor F can be negative. So the delta G is going to be negative. So what does it tell you about the spontaneity? Is the reaction spontaneous or non-spontaneous if the free energy change is negative?
Spontaneous?
It should be spontaneous. It must be spontaneous, right? Right. So if the free energy change is negative, it must be spontaneous. Now let me put another one. If I have Fe3 plus an electron giving Fe2 plus, the potential for this is 0.770. Again, plus. Reaction spontaneous? Both are spontaneous, right? Now my question here is, can I use dichromate to oxidize iron 2 plus to iron 3 plus? In other words, I'm looking at the possibility, if I have two redox processes, can I do a titration using dichromate to oxidize quantitatively iron 2 plus to iron 3 plus? Would that process be spontaneous or not? To answer that question, we need to again write the cell potential for the overall reaction where the dichromate gets reduced, so it's the cathode, and the iron gets oxidized to iron 3 plus, that's your anode. So your overall cell potential will be the cell of the cathode minus the cell of the anode. All right. So the cathode is 1.38 volts minus the anode, which is the oxidation of iron 2 to iron 3 plus. You're basically flipping the reaction. When you do that, the cell potential changes its sign. That's why we put a negative here. plus 770 volts. So if you look at that difference comes to, can anyone calculate and tell me what the difference is? 1.38 minus 0.77.
0.61.
0.61. That's a plus 0.61, right? So is that process spontaneous or not?
Yes.
Yes.
So what is this telling now? That it is possible to use dichromate to oxidize iron 2 plus to iron 3 plus in a quantitative way because the cell potential is plus 0.61 volts. Am I making sense here? So yes, the answer is dichromate can be used to oxidize iron 2 to iron 3 plus. My next question to you all is as follows. Suppose if you were to have some chloride ion in the solution, would that interfere with your titration? In other words, if I were to write the redox potential for the chloride ion, Cl2 plus 2 electrons giving 2Cl minus aqueous has a potential of about plus 1.36 volts. This 1.36 volts is very close to 1.38. So in other words, if you were to have both iron 2 plus and Cl minus coexist in a solution, would there be an interference from chlorides? What's your take on this? What would be the overall potential for the dichromate oxidizing chloride? Same way we have done for iron, right? We do the same thing for the chloride and then say this is dichromate, which is 1.38. Now, for the oxidation of chloride to chlorine, watch my words very carefully. If I have a chloride ion in this solution, I'm trying to see if there is an interference. So if you do this calculation, that is 1.36 volts, that is a mere 0.02 volts. Is that potential enough to drive a process? Those of you who paid attention to my lecture, previous one, where we talked about water potentials, and if you look at this reaction in which chlorine is a gas, so whenever you have gases involved, you need to have a potential minimum of 0.6 volts to drive the process. What you have is just only 0.02, 20 millivolts. It's nothing, peanuts. So we can say the dichromate is not going to oxidize chloride to chlorine in preference to iron 2 plus to iron 3 plus. So even if you were to have some chloride in the solution, it is not going to interfere. On the other hand, if you were to have some other contaminants whose reduction potential is very close to that of iron, they will interfere in the dichromate titration. So whenever you are doing a titration or quality control, if you are working for a mining company, they want to know how much iron 2 plus is in the mining ores, you got to look at all the other ones and do this calculation to see which ones might interfere. Am I making sense here? So to summarize, one can use the redox potentials to estimate whether or not a species is more oxidizing or easily reduced to relatively a species that is less easily reduced, like iron 3 plus 2 iron. So the general trend here is, as long as the reduction potential of the first reaction is way above, all the others below will be affected. In other words, the first one will oxidize the species on the right-hand side of them, as long as the redox potentials are smaller. So you need to practice a few things so that you'll have a good control. You just need to look at all the potentials just the way I have written down. I have broken it down very simply. And I told you where the interference is and where the interference won't be there, and when to how to calculate the spontaneity of the processes. So let's do one more problem based on this. This time we're going to talk about the effect of pH. Now, in this reaction, although we have protons, because we're talking about standard stir potential, the concentration of H plus is going to be 1 molar. But if you're dealing with aqueous water, your concentration of H plus is not going to be 1 molar. Instead, it's going to be 7 orders of magnitude smaller, 10 to the negative 7 molars. How would that affect the overall process? That's what we're going to look at. So let's look at some of the calculations here. So let me write down a reaction. Permanganate MnO4 minus plus 8H plus 5 electrons, giving Mn2 plus 4H2O, has a potential of plus 1.51 moles. This is given to you. This is the standard redox potential that you can get it from the tables. All the electrochemical tables will tell you. But what they won't tell you is what happens when the pH is not 0. What if its pH is 7? So how do we calculate the potential at pH 7? We'll assume in all these calculations that everything else remains at 1 molar except the protons, because you're doing the reactions in water at pH 7. So how do we set this up? We use what we call the Nernst equation, which basically tells us that the non-standard state potential is the standard state potential minus 0.059 divided by N, where N is the number of electrons involved in the redox process, times log of Q, where Q is the reaction coefficient. In this case, the Q basically is the concentration of Mn2 plus. Should I include the concentration of water? Do I have to know the concentration of water? Huh? John?
No.
You are correct. Why?
We never include water. It's
Because it's going to be the same in the reactant and in the product.
What's the physical state of water is? Liquid, right? When you have liquids or solids, they are not included in the reaction coefficient. Only aqueous solutions and gases are involved in the reaction coefficient. You all remember that rule, right? So if the physical state of a substance is either a liquid or a solid, they are not used in the equilibrium constant calculations. So that divided by concentration of MnO4 minus times concentration of H plus raised to the power of 8. That will be the expression. Now, as I said, the concentrations of all the others are kept at 1 molar. Only the proton concentration changes here. So that now comes to 1 mole H plus to the power of 8. Does that make sense, folks? Now, the concentration of H plus is 10 to the negative 7th of a molar. So that will be 1 over 10 to the negative 7 molar raised to the power of 8. What I want you to do now is go back to this equation So E equals 1.51 volts minus 0.059 divided by, what should be the value of N here, folks? Some of you can turn your microphone.
It'll just be 5.
It must be 5 because in this process there are 5 electrons involved. So that should be 5 times log of Q, right? Which is basically 1 over 10 to the negative 7 to the power of 8. So can somebody do a quick calculation and tell me what this value is? If I give an answer, you will lose the method of doing the calculation. So I'll give you a minute to tell me what that value is. But before you finish your calculation, would you expect the value to be more than 1.51 or less than 1.51? So whenever you get an answer, oftentimes it's useful to know whether that answer makes sense. So first let's get the answer and then we'll rationalize why it is more or less compared to the standard state potential. So I'll give you 1 minute to finish this calculation. If you have an answer, please let me know. You can turn your microphone on and tell me.
Chari, is it 0.8492?
You're absolutely correct. Is it plus or minus?
Plus?
You're absolutely correct. That is plus 0.8, approximately, can I say 0.85 volts? Because we're to about 2-3 significant figures, we can say that as 0.85. Does it make sense? That the reaction is less spontaneous at pH 7 compared to at pH 0. How do you rationalize this? Why would it decrease? I know the math tells us if for some reason you make a mistake in the math and you end up in an answer that is more than 1.51, it should immediately tell you, well, something is wrong here.
Is it because you have less protons at pH 7?
Yes. So what does that translate into? You're thinking right. That's a good starting point. So if you look at the equilibrium here, right? With the standard state, we have 1 molar. Now I reduce this concentration down to the -7. So which way would the equilibrium move? When you reduce the concentration of the reactants, the Richard-Wave principle tells us that the reaction must move from right to left. Correct? That's how it maintains the equilibrium constant. So when it moves from right to left, the reaction is not spontaneous in the way it's written. Because now it is reactant favored, not product favored. So for that reason, the value 1.51 will take a hit and come down to plus 0.89. Am I making sense, folks? Yeah. Although I gave you an example for a half cell, even if you have a full redox reaction, and if you know the concentrations of the reactants and the products, specifically about aqueous solutions and gases, if you were to have gases, their concentration is supposed to be standard state is 1 atmosphere. So make sure that you use the units of atmosphere, not millimeters mercury. Those things are not allowed here. So if you reduce the concentration of a gas from 1 atmosphere, which is the standard state, to 0.5 atmospheres, use the word number 0.5. Am I clear here, folks? I mean, the textbook, they give you lots of examples. So you can try the pH and the concentration dependence using what we call the Nernst equation. This is what the Nernst equation is. You don't have to memorize this equation for the exams, but it's good to know why this works and how to use this equation in real life examples. Any questions on this problem? This is clear enough? The steps are clear? We start with the Nernst equation and then write the expression for the Q and then substitute all the concentrations and get a value for the Q, plug it into this equation, and then calculate the potential. That's all it is. And make sure that whatever potential you get makes sense. And the way it makes sense is looking at what is changing in this equation. If the reactions are reduced in the concentration, the reaction is not going to be spontaneous because the Dirichlet principle drives the reaction backwards, making it less spontaneous. Okay? So in other words, the reverse reaction is spontaneous relative to the forward reaction. That's how we look at this. Am I making sense here, folks? Any questions? Anything that's not clear? All right, so we'll now ask the other questions about why some elements are not stable in water, while some are. So let's try to look at the electrochemical phenomena behind the stability or the instability of metals and inorganic ions. So I'm going to spend a little time. So, for example, we want to know, is magnesium metal stable in water at a pH of 7? Okay. The information that you will be given is as follows. At pH 7, the potential for that reaction is negative 0.41. And the potential for this reaction, maybe some 2 plus EPS and solid, is from the books is negative 2.35 volts. The question is, can magnesium survive in pure water whose pH is 7? Let's assume all the other concentrations are 1 molar. We don't care about magnesium because it's a solid, it doesn't affect the equilibrium. How do we do this? So for the magnesium to be stable, it should not reduce water. If it reduces water, then the magnesium gets oxidized and it won't be stable. So we're now looking at a reaction in which the magnesium is oxidized to magnesium 2 plus, and the water or the protons that are reduced to hydrogen gas. To do this, we need to again write this out. The cathodic, which is the reduction part, minus the anodic, which is the oxidation part. So specifically, we are now looking at the reduction, that is negative 0.41 volts, minus the anodic potential, which is the oxidation of magnesium, which is negative 2.35 volts. So what do we get here? What's the value? Those of you with a quick calculator can do this.
That's 1.94 volts.
That's correct. Thank you very much. What does that tell you about the spontaneity? So if I were to write a reaction, magnesium plus 2H plus, giving magnesium 2 plus H2 gas, that's what we're doing here. So the potential for this reaction is just what we calculate, 1.94 volts. What does that tell you about spontaneity? We opened this lecture saying that if the potential is positive, the reaction is going to be spontaneous. So magnesium metal is not going to be stable in water because the oxidation of magnesium is spontaneous in the presence of water. Am I making sense? All right. Questions? We're going to build up from this and slowly look at other things. This is the simplest possible thing. We're going to look at some other things, and then we will never lose sense of our common sense too when we're answering these problems. Yes, magnesium is extremely reactive. When you drop it in water, it's going to violently react and produce hydrogen. And sometimes you can get flames and, sounds too. All right, so let's look at another one. Let me see. Yeah, I do have T. Let's change the magnesium to a different metal. We'll use the same equations. The numbers are going to be different. This time, I'm going to have aluminum metal. So the potentials again are, for the first one, negative 0.41 moles, and for the second one, we have can anyone quickly check what the potential redox potential for aluminum to aluminum metal is? Yeah, I get negative 1.70 volts. Forget it, I got this one. I wrote it down smaller. So my question then is aluminum metal stable in water? Can anyone tell me what the cell potential for this is? Use the same method that you have used for magnesium and tell me what the value should be.
I got 1.29 volts positive, so it should be spontaneous.
Your answer is aluminum should not be stable in water, right? But is it what you see in regular life? Have you ever
No,
experienced
no.
sprinkle some water in aluminum foil? Does it spontaneously and violently react with water? This is where we're going to be careful. Thermodynamics tells you that aluminum should not survive in water because the oxidation of aluminum by water has a positive cell potential, which means aluminum is not stable in water. But then our experience tells us that aluminum is really stable. How do we reconcile the contrasting facts here? On one hand, we have visual observation, which tells us that there is no reaction. On the other hand, the calculation is telling you that it must happen. Does anyone have any thoughts on this?
Doesn't the equation not take into account the rate of the reaction?
That's true. That's a beautiful point. Because the kinetics and the thermodynamics is very different, right? Just because something is spontaneous, it doesn't mean that it's going to be instantaneous. That's one reason. What's the other reason? In fact, to be honest with you, the reaction between aluminum and water is almost instantaneous. It is so quick that as soon as you oxidize Al3 plus, right? Aluminum to aluminum 3 plus, if you look at aluminum foil, on the surface, you got a film of what we call aluminum oxide, Al2O3. That film is so impervious that it will not allow the next water to come and react with aluminum below that layer. For that reason, although thermodynamically it is supposed to be spontaneous, as soon as you have a nice film of aluminum oxide or aluminum oxyhydroxides, okay, and they become extremely very dense films, and all the aluminum that you have has a very fine coating of aluminum oxide. For that reason, we don't see any reaction. It's not that the reaction is not happening, it's just that the products of the reaction now are detrimental to the progress of the process. It will not allow the next aluminum to react. So these things do happen, so you have to be very careful. So what does it tell you? If I don't have aluminum foil, but if I have a fine aluminum powder, that's going to react violently with water. If I have nano-sized aluminum powder, that is going to violently react with water. However, if I have a sheet of aluminum or a foil of aluminum or a container of aluminum, it's not going to show that violent activity because of the formation of what we call passive films. This is what we call passivation of the surface. The surface gets passivated. No other reactions possible. Am I clear here, folks? So we're now looking at the thermodynamics and the reality. So that's where we have to be very, very careful. Does aluminum react with water? your answer depends on what is the physical form of aluminum. If it is a foil, the answer is no. If it is a vessel, the answer is no. But if the aluminum is a finely divided powder, yes, it does. Is that clear to all the class, folks? Any questions so far on this? Anything that's not clear? Are we okay? All right, moving on. We have a lot of problems here. The next question is, all right, we've been talking about metals and ions, but how about polyatomic ions? It's base stability. So for example, we have the polyatomic anions of chlorine and oxygen, perchlorate, chlorate, chloride, and hypochlorite. Which of these species is easily reducible? From a common sense point of view, can you answer that question? If you are cleaning swimming pools, right? What do we add? Anyone with some experience in that? Do we add chlorates, chlorides, or hypochlorites?
Don't we add the perchlorate?
Perchlorates, no. Perchlorates are very difficult to get reduced. Perchlorate oxidation is only for killing bacteria, but if you want to do a real oxygenation, you have to use ClO minus hypochlorites. So basically they add chlorine to the water, right? When you have chlorine in the water, it forms hypochlorites. So when you look at the ease of reducibility, this is how the patterns are. Hypochlorite is easily reduced relative to ClO4 minus. ClO4 minus is very difficult to get reduced. When it is easily reduced, that means it can easily oxidize to other species. So if you want to oxidize or add oxygen, this is how you have. You add perchlorides. I'll give you another process. Suppose if I have highly non-stoichiometric oxides. For example, let's say if I have something like LaMnO 2.5. This is what we call oxygen deficient oxides. Typically it should be 3, but when you heat the oxides at very high temperature, some of the oxygen leaves and the product what you get is LaMnO 2.5, which is oxygen deficient oxides. So if you want to really oxygenate them, low temperatures, what you do basically is you take sodium hydroxide and bromine liquid. What happens here is the sodium hydroxide reacts with the bromine to make what we call sodium hypobromide. This sodium hypobromide, these reactions are carried out at 5 degrees Celsius, very low temperatures. So you don't need to have very high temperature furnaces here for oxygenation. These are what we call in French, chimie douce, that is soft chemistry. So instead of using violent ozone and oxygenations, you can use simply a mixture of sodium hydroxide and bromine at 5 degrees Celsius and stir it with this compound And after about 3-4 hours, you get LMNO3, which means this compound is now oxidized, which implies that OBR is reduced. So since OBR, just like this, is easily reducible, so we can have soft oxygenation processes. All these are tools in your toolbox. When you get a job there and sometimes you have a compound that is oxygen deficient and you want to create an oxygen rich atmosphere or oxidizing atmospheres, you can use this. Trust me, it works because I've used it in the past and it works like a charm. I just put that in and then go back and come back in the morning and I have a compound completely oxygenated. And this is related to this. I will never use perchlorate for oxidation. For one reason, perchlorates are extremely explosive. So I would not touch them in the lab. Bromides are very soft, they're pretty easy to work with. All right, so this is the point here. So if you have a series of compounds, and the question is, why is that? Part of the two reasons. When you are easily reducible, that means if you are adding an electron, which of the species can accept the electron easily? If you look at perchlorate, you have 4 oxygens and a negative charge, and the chlorine is in 7+ state, oxidation state, right? Chlorine 7+ should be extremely tiny, small. So when you have a small central atom with a negative charge, the surface charge density is very high. So when you're trying to bring an electron, the repulsions are going to be so high that you will not have a reduction. But on the other hand, if you look at ClO minus, here the oxidation state of chlorine is +1, much bigger size. Remember, the size of an ion or a cation decreases with the increasing oxidation state. So chlorine here is much smaller compared to this. Cl1+ is big, but then you have the same charge. So now if you calculate the surface charge density there, it's going to be small. So bringing an electron is much easier. So that's another way of rationalizing this behavior. This looks counterintuitive, but this is the chemistry behind this. So how do we know this is the thing? So we have looked at all the other species. For example, whether size plays an important role or not can be tested by looking at, suppose if I have ClO3 minus, BrO3 minus, and IO3 minus. Which one of these is easily reducible? From the arguments that I have presented. Any ideas? You all have the same charge. You have chloride, bromide, and iodide. They have the same negative charge, but which? Yes, Serena.
Are you asking which one will be the biggest?
You are absolutely correct. So between these three, which one is easily reducible?
Iodide.
You are absolutely correct. It's not iodide, iodite, right? And so this is how the thing goes on. So let's see some other things. So this trend happens whether you have chloride or perchlorate or chloride or hypochlorite. Even if you have, let's say, ClO minus, BrO minus, IO minus, if I'm comparing these three species, it's clear that IO minus can be easily reduced compared to hypochlorite. The problem is the stability of the iodide. That's the reason why we use hypobromides for oxidation, not hypochlorites. Ideally, this should be the easily reducing. That means highly oxidizing. Let's look at other polyatomic ions and then see the stability in the water. So next one is, let's say if I have this species. Which of these species is easily reducing? That means which one is a strong oxidizing agent? That's another way of asking the question. Strong oxidizing agents are those that are easily reduced. So we now have chlorine, sulfur, and phosphorus. So what's the oxidation state of chlorine here, folks? +7. How about sulfate? Oxidation of sulfur is in sulfate.
+6.
+6, you're correct. Thank you. How about HPO4 2 minus? Monohydrogen phosphate.
+5.
+5, you're absolutely correct. So which oxidation state gives a larger size? So if I have something 7 plus, 6 plus, and 5 plus, which one is generally bigger?
The 5+.
You're absolutely correct. So bigger the size, the easier it is to be reduced. So between these species, HPO4 2 minus, relatively speaking, compared to the perchlorate or sulfate, monohydrogen phosphates are easily reducible. Am I making sense here, folks? This is clear? I mean, one way you can also say that because the HPO4 can add on to another proton to make dihydrogen phosphate, H2PO4, 1 minus. So addition of hydrogen is almost like reduction, right? So it's easily reduced here. On the other hand, the hydrogen association with perchlorate is not strong. It's not easy to add protons because perchloric acid is a very strong acid. It doesn't want the protons. It kicks the H plus out. That's the reason why it is a strong acid. Another way of arguing the same thing. You see how we are bringing in acid-base chemistry to the redox chemistry here. Any questions on these things? Okay, so far. We gave you both qualitative and a possible hypothesis on predicting the stability of the oxo anions in water. These are all oxygen-containing anions, and we now have a way of looking at their stabilities. All right. Next topic is what we call non-complementary processes. In general, non-complementary redox processes are slow. But before we answer why, we need to know what exactly is a non-complementary redox process.
It's frozen for me as well.